In this video, I'll show you how to solve the ALEKS problem called calculating reaction-free energy under non-standard conditions. This problem is actually pretty tedious. There's quite a few calculations that you have to do to solve this problem. The equation that we're going to use to calculate the non-standard free energy, non-standard delta G, is delta G non-standard equals delta G standard plus RT ln Q. In order to solve this problem, we need to know or calculate the value of standard delta G, and we also need to know or calculate the value of Q. And since this problem is not giving us either of these values, we have to begin by calculating both of them. To calculate standard delta G, we are going to use the balanced equation that's provided to us. We're going to use the Hess's law strategy, so I'm just going to make a note of that here. In Hess's law, we are going to be following the formula of products minus reactants, each multiplied by their stoichiometric coefficients. So looking at the balanced equation, we are going to take the delta G for our products, and we are going to subtract from that the total delta G for all of our reactants. These delta G values that we're going to be using in Hess's law can be found here in ALEKS in the data tab. You just click on that. And then once you're inside, once you've opened up this screen, you're going to look for thermodynamic properties of pure substances. And in that data table, you're going to be looking for the delta G of formation values. You've probably already done that, so you probably already know. I have these values pulled up on a separate computer so that I don't have to open this screen up and clog up all this space with ALEKS's data. So I'm just going to be plugging those numbers in, starting with my product, which is NH3 gas, and I have two of them. Remember, we have to multiply these by their stoichiometric coefficients. And then on my other computer right now, I'm scrolling and looking for NH3 gas. And you got to be careful, make sure that you are matching the state of your substance with the data table, because in the data table, NH3 is listed as both a liquid and a gas. So for NH3 gas, the value is -16.4. And the units of this are kilojoules per mole, but I'm going to leave the units off just to save space, and I'll add the units when I'm totally done with this calculation. So there's my products, and then from that, I'm going to subtract my reactants. I have one N2 gas, and so I'm going to look for the delta G value for N2 gas. It's 0. And then my other reactant is H2 gas. There are 3 of them, and I'm going to look for the value for H2 gas. That one is also 0. So that makes this a pretty straightforward calculation. And so for this, I'm going to use the calculator because I don't want to mess this up. I have 2 times -16.4, which is -32.8. And remember, the units on this are kilojoules per mole. There. So that takes care of this part. Next thing that we're going to do is calculate the value of Q. Q is the reaction quotient, and you calculate it the same way that you would calculate an equilibrium constant, K. That means that we are going to take the concentrations of our products, each one raised to its own stoichiometric coefficient, and we're going to put that over our reactants, again, each one being raised to their stoichiometric coefficients. Now, actually, I should have looked in this problem. It looks like it's giving us, instead of giving us the molarities of these substances, it's giving us pressures. So these are actually going to be pressure values instead of molarity values, and I should have checked that before I wrote all of this. So we're going to take the pressure of NH3 and raise that to the stoichiometric coefficient 2 from the balanced equation, and then that's going to go over the pressure of N2 and the pressure of H2 raised to its stoichiometric coefficient, which is 3. And then we are going to be plugging in these pressures from the problem. The pressure of NH3 is 4.55. Again, I'm just going to be leaving units off to save space, 4.55. The pressure of N2 is 5.03, and the pressure of H2 is 7.47, and that one needs to be cubed because of its coefficient. 4.55 squared divided by 5.03 times 7.47 cubed. And this is 0.0098. I'm just going to leave a few sig figs on there. 0.9874. Hopefully I entered this into my calculator correctly. It looks like I did. That's the number that you get. Now the value of Q is a unitless number. So leaving the units off of here was totally legit. We have no units over here. So now we've got this number calculated and we're ready to plug everything in to get the value of the non-standard delta G. Remember, I told you this is a pretty tedious problem. So I'm plugging in now at this point. Delta G, I calculated that to be negative 32.8 kilojoules per mole. And the value of R that we want to use for this problem is 8.3145 joules per mole Kelvin. Remember, we have two different versions of R. One of them has units of liters, atmospheres, mole Kelvin, and that unit or that value of R we don't want to use in this problem because we want consistency with our units here. 8.3145 joules per mole Kelvin. T is the temperature, which is 25 degrees C, and that needs to be in Kelvin because that's the temperature unit that we're using in this problem. So that's going to be 298.15 Kelvin. 298.15 Kelvin, and then the natural log of our value of Q, which is 0.009874. And I'm going to just make a little bit more room for myself here. So I'm just going to copy the negative 32.8 kilojoules per mole, and I'm going to work out the math over here on this side of the problem. I'm just going to start with this part. Take a look, first of all, that the units of Kelvin are going to cancel out. So I'm going to go 8.3145 times 298.15. That's going to give me 2479. Here I'm rounding a little bit, joules per mole. And then that number needs to be multiplied by the natural log of 0.009874, which is negative 4.618. That is going to give me, I'm just kind of trying to go a little slow here on the math because it's a lot of places where we can get stuff messed up. I'm going to work out the multiplication on this part. 2479 negative 11448 joules per mole. So I've just copied this number and then also I worked out the math right here, which gives me this number. Now we have a pretty minor issue here with some inconsistency with our kilojoule versus joule situation. And I need to make myself even more room. Let me squeezing this up. And so for this, you have the choice of either converting your kilojoules to joules or the other way around. If you notice, the ALEKS problem wants the answer to be expressed in units of kilojoules. So I think probably the easiest thing is going to be to convert my joules into kilojoules. That's going to be negative 32.8 kilojoules per mole minus 11.448 kilojoules per mole. I'm just dividing by 1,000 over there. And that is going to give me an answer of negative 44.2. It looks like the answer, ALEKS says that it wants the answer to the nearest kilojoule. So assuming that I didn't make any calculation errors, any rounding errors, things like that, there's my answer. Now notice the ALEKS unit is just kilojoules, not kilojoules per mole. And sometimes that happens in terms of like, sometimes that the per mole part is left off. Don't even stress about that. I'm getting kilojoules per mole over here. Essentially, it's the same thing as just kilojoules. So the answer that ALEKS is looking for is negative 44 kilojoules.